Fairly often, I get asked questions about how I got started podcasting with the Breaking Math podcast, and I'll often be asked this question by those who are thinking of starting their own podcast. That is, people who are looking to tell a story or share their unique wisdom with a larger audience or their passions, or maybe just advertise their business or services. I usually like to start this conversation by either showing off or telling about our preferred podcasting platform, Zencaster. Zencaster is essentially an all-in-one podcast hosting platform. On this platform, you can do everything from recording your episodes to editing your audio and video files to distributing your podcast to all podcasting platforms, including Apple Podcasts, Spotify, iHeartRadio, and wherever else podcasts are played. Now, there's more. When I first began podcasting, I used to get very nervous about how I would sound. I would sometimes stutter or have awkward pauses or other audio blemishes in my recordings. Now, Zencaster has a new suite of AI tools in their post-production process that make you sound really smooth. They automatically take out any of the ums or ahs in your recording. Also, they automatically take out any of the awkward pauses in your discussions. The tools will also help you set the right loudness and balance all the levels while reducing any background noise, all with the click of a button. Doesn't sound too bad, does it? You really should check it out. Really, the world needs to hear what you have to say. In fact, I'm going to give you a code below to help give you a large discount. It's all one word: Breaking Math. Go to zencaster.com/pricing and use my code Breaking Math, and you'll get 30% off of your first month in any Zencaster paid plan. I want you to have the same easy experience I do for all my podcasting content needs. It's time to share your. People very often ask me both how and why I started my podcasting journey. Well, as an engineer, I'm frankly very passionate about math. I wanted to find somewhere to share stories of great mathematicians from Archimedes to Alan Turing and everyone in between. And for that reason, I want to tell you a little bit about my preferred hosting platform, which is Zencaster. Now, before I continue, this is usually the conversation I have with anybody who is wanting to start their own podcast. I know there are so many people out there with passions that they want to share with the world or unique knowledge that they're just looking for a platform to start with. And Zencaster is a wonderful all-in-one platform. What I mean by that is you can do your recording and your editing and use AI to create a transcript and distribute to all platforms, including Apple Podcasts or Spotify or anywhere else where podcasts are played. For anybody like me who might worry at first about what you might sound like on an audio recording, Zencaster's post-production process makes you sound really, really smooth. It automatically removes any of the ums or ahs in your recording. It removes any of the awkward pauses in conversations, and it also helps you to set the right podcast loudness and levels while reducing any background noise, all with the click of a button. It couldn't be easier. Go to zencaster.com/pricing and use my code BREAKINGMATH, and you'll get 30% off your first month in any Zencaster paid plan. I want you to have the same easy experience I do for all my podcasting and content needs. It's time to share your story.
In introductory geometry classes, many of the objects dealt with can be considered elementary in nature. Things like tetrahedrons, spheres, cylinders, planes, lines, and other such concepts are common in these classes and are part of classical geometry. However, we often have the need to describe more complex objects. These objects can be quite organic or even abstract in shape and include things like spirals, flowery shapes, and other curved surfaces. These are often described better by differential geometry as opposed to the more elementary classical geometry. One helpful metric in describing these objects is how they are curved around a certain point. So how is curvature defined mathematically? What is the difference between a negative and a positive curvature? And what can Gauss's Theorema Egregium teach us about eating pizza? All of this and more on this episode of Breaking Math. Episode 58, Bringing Curvy Back. I'm Sophia.
And I'm Meryl.
And you're listening to Breaking Math. Meryl's been on quite a bit recently. She was on, what episodes were you on recently?
I was on the one about spheres and the one about bases.
Yeah, and Meryl is actually going to be part more of Breaking Math now, and she's going to be a co-host as well. So this is sort of a welcome of Meryl to that part of the show. Before we continue, let's do some plugs. If you want to support the show monthly, you can support us on Patreon at patreon.com/breakingmath. $1 or more will get you outlines that we use for the show, and which sometimes can have diagrams and stuff on them that are useful. And you can find our episodes without advertisements there. If you want to find updates about the show, you can find them at facebook.com/breakingmathpodcast, or more commonly now our Twitter at breakingmathpod. Our website is breakingmathpodcast.app, breakingmathpodcast.app. And it's under construction right now, but it's still usable. And if you want to email us ideas, comments, questions, or corrections, you can email us at breakingmathpodcast@gmail.com. And if you want to listen to something quite like Breaking Math, you could listen to our sister podcast, Turning Rabbit Holes. So Meryl, do you want to walk through the difference between classical and differential geometry?
So what I would say is we're talking about, with more classical geometry, think Euclid, lines, angles, certain polygons, and theorems involving those.
Yeah, and Euclid had, like, in elements, everything is based on a few axioms. It's a very heavily...
Right, the postulates.
Yeah, it's a very heavy postulate/axiom, whatever, based system. But differential geometry, it doesn't really have axioms per se, right?
Well, what we're really thinking of here is where more classical Euclidean geometry is to Euclid. In this case, we're working with differential geometry, which I would say is more of Gauss's realm.
And Gauss is an interesting character. Isn't he the one that added up the numbers from 1 to 100?
Oh yeah, that formula.
Yeah, he was in like second grade, and he was annoying his teacher. So she was like, add up the numbers from 1 to 100. So he wrote 1 plus 2 plus all the way to 100. And then he wrote it backwards, and they noticed that every entry added up to 101, and he just multiplied that by how many there were and divided by 2, and got the answer in a few minutes.
So Gauss did work a lot with surfaces in three-dimensional space, particularly, things like spheres or other curved surfaces, integrals or differentiation among them, and theorems relating to such.
All right, so what is curvature, basically? I mean, we could define it in terms of oscillating. They're called oscillating circles, and I think we have a good example for describing kind of what that is.
So the concept of describing curvature using oscillating circles can be attributed to Cauchy, and pretty much what that is you have... So let's say you have a one-dimensional curve in two-dimensional space.
So this could be like, for example, if you're driving on a path, like on off-roading or on a road, right? If on a flat surface, or even a 3D surface, right?
Yeah. So kind of like it's like a parametric curve is what you're thinking there.
Yeah, like you have a point and you have a location is in space over time.
So going back to the concept of oscillating circle, so pretty much what we're doing is, so at any point on this path, so draw a circle where exactly one point touches that point on the curve, and then just keep expanding the circle until, if you expand it any bigger, it would intersect at more than one point. And so that biggest possible circle you can fit into that part of the curve is called the oscillating circle. And the curvature at that point can be described as the reciprocal of that circle's radius.
Yeah, so, to clarify too, the circle has to be expanded until it intersects local points, right? Because I was thinking if you have kind of imagine if you took a shoelace and you made a kind of a flat oval, but then pulled it back through itself, the oscillating circle would intersect more points on the shoelace than one, right?
Right. So we are kind of thinking more on an infinitesimal level. So let's say that we have a short stretch of the plane that is a straight line, then the radius of that oscillating circle would technically be infinity, because you can just keep growing and growing, and it would not ever intersect at that local neighborhood.
Yeah, it's a kind of a weird thing that we've been coming back to in Breaking Math recently. It's describing circles in terms of lines. It's just kind of tangential to that. But so one example that I came up with for describing curvature is talking about like if you're on a car driving on like, let's say a salt flat, right? So if you drive in a circle, you will feel a pull, right?
Right, the lateral G's.
Yeah, the lateral G's towards the center of the circle. And if you notice that if I'm driving, let's say like 30 miles an hour, if the circle is really big, like a mile wide, I'll barely feel any acceleration, right? But if it's like a really small circle, like 10 feet wide, I would probably like start to throw up if I'm going 30 miles an hour.
Yeah, so you start doing donuts, you're really going to feel it. And that can kind of correspond to curvature, is the more lateral G force you feel, the more curvature you would be getting. As you're talking about, like if you're moving along a curve, then you have some amount of acceleration towards the center of, and I guess in this sense, we could call it the osculating circle.
So let's say I'm driving along a weird path in a car, right? So like, let's say I'm tracing out, a picture of a duck on this salt flat. If I want to know what the curvature is at a certain point on the duck, all I have to do is freeze my hand so that the wheel stays still and the car will go in in the oscillating circle. So it's just kind of another way to look at it. And then if you measure the acceleration in the car, which can be done by weighing something. All right, so now since we've done curvature, the next part is going to get a little bit into linear algebra. And so before we do that, let's talk about the concepts really quick. All right, Meryl, what's a vector?
So there's a number of ways to define a vector. Some people will call it a rank 1 tensor, or say it's a quantity that has magnitude or direction. But all we really need to know in this case is that it is, for our intents and purposes, a collection of real numbers.
Yeah, and these numbers, we through some way, there's many ways to do this, different types of coordinates and whatever. But these numbers describe, in some way, magnitude, direction. All these things are relevant, definitely. Yeah, a vector will have like let's say we're just in 3D Euclidean space, right? It'll have usually it'll be the vector x and the vector y and the vector z, right, as the basis.
Oh, you're talking about like, orthogonal basis vectors. Okay.
Like if we're measuring like space for real, we have to have like like a point of reference and like what a unit is and all that.
Something that I kind of glossed over because I said it was a collection of real numbers. Something that I think I need to clarify on is that it is going to be like whatever dimension space is in is how many numbers are in that vector.
Oh yeah, and so yeah, if you're in 4-dimensional space, no matter what system you use, you have to define it using 4 real numbers.
4 linearly independent real numbers.
Yeah, that's right. Because if you have 2 axes pointing in the same direction, then basically, like if you're in 3D space, you'll only be able to describe things on either a plane or a line, depending on how linearly dependent the vectors are to each other, right? The basis vectors, or the fake basis vectors that don't actually work as basis vectors.
Yeah. So it just they have to span the whole space, is all that means.
Yeah, and I mean, some basis vector type concepts that we use in daily life is like north and south. But also, would you like to describe how velocity, for example, can be described by a vector?
So velocity, and this is the high school physics definition, is that it's not just speed. Speed is just the magnitude of velocity. Velocity is the speed that something's going at and the direction that it's going.
Yeah, so if I if somebody shoots an arrow, the velocity points along the direction that the arrow is flying, right?
Right.
And the acceleration can also be described by a vector. And the acceleration is like what you would feel if like you were in like a carnival ride, like the way that your stomach is being pulled left and right. Can be described by acceleration, and the direction that you feel the pull is the vector in that situation, and then magnitude is how much you feel the pull. So I think that kind of describes vector as well. So next we're going to talk about what matrices are and how they can be used to transform vectors. So let's say, to describe what a matrix is, let's say I have a sphere made out of vectors, right? Like basically vectors pointing in every single direction, and they can be described by arrows that are of length 1, right?
Right.
So there's a few things I could do to that sphere. I could stretch it so it turns into an oval, right? I can skew it. I can make it bigger and smaller. Scaling is just stretching equally in all directions, right? So if you want to describe all these things, they're called linear transformations, and they're called linear transformations for one of many reasons. One is that a line multiplied by a matrix will just be another line, right?
Right. So for pretty much every normal vector on the sphere that you have, when you're mapping it to something else, there's, a constant scaling associated with it effectively for whichever direction you're pointing in.
Yeah, and so you're talking about the direction of the stretching and stuff, right?
Right. And, that's why it's called linear, is because that scaling is for any one direction. It's constant. It's not, it's not squaring or cubing or, something weird like sinusoidal or exponential.
Yeah, and also like many linear transformations can be reversed, inverted, so just transformed back. The only times really where they count is when you compress the amount of dimensions they have. You can't really get that information back, right?
Right.
So let's say you have a vector, right, and you're stretching the sphere of vectors. If you look at where the original vector was, the place where that point is stretched out to, describes where the vector is when multiplied by that matrix. And then if the vector is longer than that, you just multiply it by how long the vector is divided by 1 or whatever. Because remember, the sphere has a radius 1.
Exactly.
And so also when you stretch this, you'll notice that some vectors might change size, but there's always going to be like if it's like 3-dimensional space, there's usually 3. 4-dimensional space, there's usually 4 vectors that don't change direction when they're scaled, right? And those are known as eigenvectors. Eigenvectors are a weird concept, but we're going to use them in talking about Gaussian curvature, which is really kind of like a 3-dimensional or n-dimensional really description of how things are curved. And eigenvectors and eigenvalues relate to what linear transformations are, correct?
That's right, because eigenvectors are the vectors in your domain of your linear transformation that do not in any way get distorted other than scaling by the linear transformation.
And what do you mean by domain in this context? I just wanted to clarify for the listeners.
So let's say that we are just in 2-dimensional space on the plane, like we have a painting or something, and we're applying a linear transformation. So it's going to do some, stretching and some shearing to it, but there's going to be a particular direction, a particular vector along this painting that doesn't get sheared, just scaled.
Yeah, and by the way, shearing, I'm not sure if I described that well earlier. If you want to shear a stack of cards, all you have to do is kind of like put them at an angle, right?
Right.
So yeah, that's what shearing is. I think I called it skewing earlier by accident. But so the eigenvalues is related to the eigenvectors, right?
Yeah, because eigenvalues are just, so for those vectors that I described that only scaling happens along them, eigenvalues tell you how much scaling happens along those vectors.
And what does an eigenvalue of 0 mean?
So if you have an eigenvalue of 0, that means you have a transformation that loses a dimension. So you're compressing, and so you have a linear dependence somewhere probably.
Yeah, so let's say we're working in 3 dimensions, right? And we have 2 eigenvalues that are 0. That would mean that we reduce everything to something along a line, correct?
Right.
And 3 eigenvalues being 0, I'm pretty sure that just means that you're working with the 0 matrix, right?
Yeah.
Which is a matrix of all zeros. Oh, and also matrices can be described as like a column, like rows and columns of numbers. So like transformation matrices that transform from like 3 dimensions to 3 dimensions would be 3 wide and 3 high, right?
Exactly.
But that's not totally important to what we're talking about today, except all you have to know is that if you want to look at matrix multiplication, you could do it on Wikipedia has a pretty good article. I mean, essentially, it's just you take the rows of the matrix and multiply it by the vector. You multiply it component-wise by the vector and add them all up. And then you put all those in a row, and that's the product, right?
That sounds about right.
So let's talk about real quick what the gradient is. The gradient is sort of a way to take the derivative of a vector, right?
So the gradient itself is a vector of partial derivatives, effectively. And so let's say that we have a scalar function that takes in a vector, then what we're doing is we're taking the partial derivative with every vector component, and out of that, we're getting a vector of each of those partial derivatives. And that actually tells us, so let's say that we're in 2 dimensions, just like on a plane. So our scalar function on this plane is going to look like a surface, right? Sort of like a wrinkled up bed sheet, let's say.
Yeah, or you could even say so it would describe the height, right? So you could almost say that you could even describe it as a topological map, right?
Or topographic.
Topographic map, sorry. Yeah, like one of those mountain maps.
Yeah. So what I'm kind of getting at here is that, so the gradient vector, for one thing, it tells us what, at any point, the direction of the steepest ascent is, but it also gives us a vector that is tangent to our surface. And so tangent to our surface means that, so if you draw a line in the direction of this vector, it's going to touch locally at exactly one point, and it's going to show us what the slope is at that point.
And which direction is the gradient pointing? Because obviously the slope, the gradient could be any. There's a whole circle, right, of vectors that could be tangent to a certain point, right? So which one does the gradient describe? Oh yeah, that's right. You already said point of steepest ascent. So. Yeah, so if you have a topological map, a topographic map, is probably not the best way to go about it. But if you want to climb a mountain as steep as possible, just take the gradient and then follow it up to the highest point.
I bring the gradient up because it's motivation for the tangent vectors on other surfaces, not just these scalar function surfaces, but say like parametric surfaces in three-dimensional space. Those will have tangent vectors on them as well.
So something that's tangent to like a 2D line, that would be something that points along the line, correct?
Yeah. And so we have a one-dimensional way of describing this, is that a line is tangent to a curve so it'll just touch at that one point and it'll share the slope at that point, but not necessarily anywhere else. And so when we're going to surfaces, so we have something similar. We have tangent vectors. So tangent vectors are on a plane that touches a surface. It's tangent to the surface, and it can be any vector on that plane.
So let's say that we're talking about a human head, right? And you have a book, and somebody's rubbing a book on their head. The plane that represents the surface of the book would be tangent to each spot that touches that person's head, correct?
Right. So let's say you have a book on someone's head, and so if you were to draw an arrow from the point that the book touches your head just to anywhere on the book, that's a tangent vector.
Yeah, and all these tangent vectors together describe something called the tangent space, correct?
Right. And so what the tangent space really is so for every point on a surface, we have a copy of the plane or n-dimensional space that the surface is for that point. So let's say for a sphere, for instance, we just pick any point on it. And so we put a plane tangent to that point. And then so any vector that exists on that plane is part of the tangent space for that point.
Yeah, so you're saying, so basically to sum that up, you're saying that every point has a different tangent space. So you could imagine it as like every point on the head has a different orientation of the book, and the points that like you said that radiate away on the book from the point that it touches that person's head would represent the tangent space.
What's the easiest choice you can make? Window instead of middle seat? Picking a vendor who sends a great gift basket? Outsourcing business tasks you hate? What about selling with Shopify? Whether you're selling a little or a lot, Shopify helps you do your thing, however you cha-ching. Shopify is the global commerce platform that helps you sell at every stage of your business. From the launch your online shop stage to the first real-life store stage, all the way to the did we just hit a million orders stage. Shopify's there to help you grow. Whether you're selling scented soap or offering outdoor outfits, Shopify helps you sell. Wherever and whatever you're selling, Shopify's got you covered. Sign up for a $1 per month trial period at shopify.com/try. Go to shopify.com/try now to grow your business, no matter what stage you're in. Shopify.com/try.
Yeah, and just a reminder that so the vectors in this tangent space, they can have any magnitude and direction. They just have to be on that plane.
All right, so now let's say somebody uses a pin to pin that book to that person's head. That pin would be normal to the person's head, correct?
Right, and so let's say you have any two tangent vectors at a point. So any two vectors that are not the same vector and are not linearly dependent. So let's take a vector that is perpendicular to them that would be pointing outward of the surface. It would be perpendicular to the surface effectively.
Yeah, and linearly dependent would mean
In this case, it would mean that they're either pointing in the same direction or the opposite direction. So we just don't want that.
Yeah, makes sense. So yeah, that's what the normal of a surface is. It just who's that horror movie character with all the nails in his head? Hellraiser, apparently. Yeah, so the Hellraiser guy has a bunch of nails tangent, normal to the surface of their skin, right?
Exactly.
So let's say we want to describe some weird surface in 3 dimensions, right? We could do something called parametrization. And parametrization in 1 dimension could be like a point where it is in time, right? But parametrization in 2 dimensions is like, let's say that we're doing the surface of like somebody's head, right? Again, you could define it in 2 dimensions, in 2 ways. You could say that the very top of their head is to the very bottom of their chin is like an axis, and you could say that the angle so if they're wearing a fez, for example, that hat with the tassel, the place that the tassel would go on their head. So the angle that you have to rotate that tassel to get to the point can be one parametric variable, like u, for example, or theta or something like that. And then v could be, or h or whatever, could be the height where it is on your head. So your eye would be about 5 inches down or 4 inches down from the top of your head. And it would be relatively close to 0 rotation, a little positive or a little negative, depending on which eye you are at. So that's a way to parametrize the head.
Okay. And I just want to interject and say, we really seem to be talking a lot about heads today.
Yeah, I don't know if it's...
It's all in your head. Okay, so with a lot of big definitions out of the way, now we can finally get to the main course of this episode, and that is Gaussian curvature. And so what that is so there's a handful of ways to define it. I will start with the one that says that it's the product of principal curvatures at some point on a surface.
So what is a principal? What would be the principal curvature, for example, on a paper towel roll?
So a paper towel roll would be a cylinder. So let's say curving inwards is defined as positive, outwards as negative, just for simplicity's sake. So the circular part, so the part that's going around, could be considered one direction that we're going in, and that would have a positive curvature. The other that we would have was so along the cylinder going back and forth, and so that would be in a straight line, and we call that 0 curvature.
And 0 times anything is just 0, and that checks out, because if you remember from when we've talked about curvature before, okay, let's say you have a Mylar balloon, right? You blow it up, but the balloon doesn't stretch. But the curvature of the Mylar balloon, so the curvature of the Mylar balloon doesn't change no matter how it's crumpled up or deflated. In the same way, the curvature of a piece of paper doesn't change if it's crumpled up. and or like shaped into whatever. So since you could take a piece of paper and wrap it around a cylinder, it has no curvature.
Exactly, because if you have an axis of principal curvature that is 0, that means it's going in a straight line, and that's just what we call 0 curvature, is a straight line, just like in our original definition of curvature for just a path in a 2D plane.
Yeah, and you might be wondering at this stage, like let's say you draw an X on the paper towel roll, it would seem like you have two curvatures multiplying by together with the same sign, right? Which would mean positive curvature. So one way you can find the Gaussian curvature uses what's called a shape operator, right?
Yeah. So the shape operator is going to give us our principal curvatures by using eigenvalues and eigenvectors like we talked about. And so what we're taking eigenvalues and eigenvectors of is called the shape operator.
Yeah, and the shape operator operates on the normal, the normals, right, to the surface. So, and the way that it operates the way that it operates on them is you take the Jacobian. Do you want to describe quickly what the Jacobian is?
So, the Jacobian is pretty much a vector calculus way of thinking about derivatives. Is that so? If you have a function from 3-dimensional space to 3-dimensional space, so you're taking partial derivatives of each component of our function.
Yeah, it's like a vector. Remember, matrices are like rows of vectors that you each multiply by the vector that you're doing to get to get each component, right, of the new thing. So the Jacobian takes the gradient, or the method of steepest descent, or basically of each component of the transformation of the function from that we're describing from like 3 dimensions to 3 dimensions, or 7 to 7, or whatever.
Yeah, and so what'll happen then is that each row of a matrix will be one of the gradient vectors for that particular component.
Yeah, and what happens if you take the normal of if you take the shape operator of the normal at a certain point, like, so let's say we're doing a cylinder, we actually get a Jacobian that has a row of 0, and that means that the determinant of the Jacobian, let's talk about what that means. It means that that if we have a sphere, right, that's on the surface, that's like touching like a bead on the surface of a cylinder, and we multiply it by the Jacobian of the normal at that point, which is the shape operator, right? We're gonna get a flat disk on the surface of the cylinder, and that flat disk has volume 0, which actually corresponds to 0 curvature. Basically, your transformations don't change in the up and down direction or the left and right direction, and then forward to back, you don't actually do anything.
Yeah, so let's actually get to our definition of Gaussian curvature in terms of product of principal curvatures. So each principal curvature is an eigenvalue of the shape operator.
Yeah, and in the cylinder, you get it that the eigenvalues are 1 and 0. Versus if you do a sphere, for example, I mean, in the example that we did, you get the curvature being 1 over r, because it's the determinant of that Jacobian.
Right, and so that's the other definition we can use for Gaussian curvature is, so we get product of those eigenvalues or principal curvatures, or we get the determinant of the shape operator. They come out to the same thing.
And remember, the determinant is like the new volume that this, like, you remember we were talking earlier about transforming the sphere of vectors, the one sphere of vectors. If you transform that and you get like a certain different volume, that volume divided by the original volume is the determinant. That's how it could be seen. Is the change in volume. So if you have a sphere, for example, the shape operator points into the sphere and then up and down, and the one that points into the sphere is 1 over r, I believe, in magnitude.
Right, and because the radius of the sphere is going to be positive, that's going to be positive too.
And yeah, so that's how you get the principal curvatures, and yeah, like you said, you multiply them together and you get the Gaussian curvature. How would you apply this to a saddle, for example?
So if you just hold it in front of you, then you'll see that going one way, side to side, for instance. So it would be curving up. But from front to back, you'd see that it kind of has that instead it curves down.
Kind of like a Pringle.
Right. So that means, and it doesn't really matter which one you define as negative or positive, because one will be negative and the other will be positive, and you'll multiply those together and get a surface with negative curvature.
Now, why is the curvature of a torus different on the outside and the inside?
Okay, so let's say that you pick a point on the outside of a torus.
A donut shape.
Yeah, so it's going to curve in the same direction. So it's going to curve the same way. It's going to curve, we'll call it inward, for both if you go around it horizontally or around it vertically.
Yeah, so I mean, like the way you could see that is like on the point on the outside, like if you hold your donut, you could hold it so that you're holding it by the side of the donut, and your fingers will curve like that. If you rotate your hand, your fingers don't have to curve backwards unnaturally to hold the donut sideways.
Right, so let's think about the inside of the donut though. So on your vertical axis again, so it's still curving the same way, but on the horizontal axis it isn't. It's, I guess if we call the vertical curving inward, then we would have to call the horizontal curving outward.
Yeah, and if you think about it, if you had a really big donut, you could kind of nestle some Pringles in there, right?
I guess you could.
But on the outside, they would stick out all weird.
That makes sense, although I'm not sure Pringles and donuts together are that good a combination.
Oh, they're not. Math is full of terrible combinations. And so, what can we do? What can we do with the concept of curvature? Like, what can we apply this to?
So one thing that we can do is we can find out what kind of geometry a surface has. We can find out what version of, say, Euclid's parallel postulate that a surface follows.
So there's a really elegant version of the parallel postulate that we can use for this.
So say we have a line L and a point P that is not on line L. Then, so what we're used to is Euclidean geometry, so the regular Euclid's parallel postulate that says that we have exactly one line M that P is on that does not intersect with L. So we have one parallel line to L for any point.
Yeah, and if I rotate that line at all, right? Like if I change what line it is, it's going to touch at some point, right?
Exactly.
Now, let's say we're on a sphere. How does this postulate change?
So we can think of the lines per se on a sphere as the great circles of the sphere. So all of the circumferences.
Yeah, the great circle is the biggest circle that could fit around a sphere, right?
Yeah. So that's the thing, is that if you have one of these and you have a point not on it, you try to draw the biggest circle around and you're going to intersect at that point. So for spherical or elliptic geometry, there are no parallel lines.
This is called the rubber band ball principle. Just kidding, it's not, but it should be.
And then finally we get, honestly, the best part of geometry, if you ask me, is hyperbolic geometry. So hyperbolic geometry tells us that if there is a point P not on line L, then there are infinitely many lines not intersecting L that go through P.
Now, are there there are lines that do intersect L, right?
Oh yeah, absolutely. It's just that there's infinitely many that don't. So how does this relate to the curvature of a surface? Well, something that we know about these different geometries is, so how many degrees does a triangle add up to in Euclidean geometry?
Half a circle.
Right.
So 180.
Yeah. So we can think of what curvature is doing, whether it's negative or positive, is giving us a deviation from 180, because a consequence of these parallel postulates of elliptic and hyperbolic geometry is that the angles of a triangle in, say, elliptic geometry will always add up to more than 180 degrees.
So an example of this is if I go to like the equator, like Panama, and I walk or I hovercraft all the way up to the North Pole, and then I hovercraft down to, I don't know, probably somewhere in Africa,
Like Equatorial Guinea.
yeah, Equatorial
It has
Guinea.
equatorial in the name.
Yeah, and then go back to the place near Nicaragua or whatever we were.
I guess it would be Ecuador.
Oh yeah, yeah.
Again,
Oh,
yeah. Equator named places.
Yeah, I forgot about that. But yeah, so you basically turn right 3 times, which is 270 degrees,
Yeah.
or nearabouts there.
And so what's cool about this is positive curvature, positive deviation from 180 degrees.
And negative curvature, negative deviation.
Yeah. So, in fact, in some extreme cases of hyperbolic geometry, you can actually get a triangle where all 3 angles, and this is called an asymptotic triangle, all 3 angles are 0 degrees, and you have a 0-degree triangle. So I mentioned the 0-degree triangle, but usually what we get is just a saddle surface, and so that's going to have some negative curvature, not necessarily enough for us to have that asymptotic triangle. But if you try to draw lines, so geodesics along, which are the lines of shortest distance along the surface, then you can use them to get a triangle with angles that add up to less than 180 degrees.
So now the other one was the main course, right? So this is what, the dessert?
So this is what I was really looking forward to mentioning on this episode, is Gauss's Theorema Egregium. And so that's just Latin for remarkable theorem. So let's say that we just take any surface, say a piece of paper, and so we bend it however we want. We don't stretch it at all, we just bend it. We make sure that all of the metrics on it stay the same effectively. Then the curvature on it doesn't change.
Even though it's locally curved, right? You're saying that the intrinsic curvature doesn't change, because like if you wrapped it around something, you could say that, you know, if you follow a path along that line, it would be curved, but the intrinsic curvature, therefore, it's such a remarkable thing, you know, because it could be measured no matter how it's embedded. I mean, you could also think of this as like a deflating balloon or deflating anything like that. Specifically a balloon that doesn't stretch, like a mylar balloon, or like a balloon for like a what do you call those balloons that people ride in? Just a hot air balloon. I should know this. I'm from Albuquerque, but I lose 10 Albuquerque points, 10 green chilies. But yeah, when this deflates, the curvature does not change just because it's deflated. Because if you think about it, like if I have a globe or an orange peel, I can't really flatten an orange peel onto a table without basically cracking it everywhere, right?
Yeah, and so let's think about that for a second. So an orange is a sphere, yeah?
Usually, just gonna guess.
Spheroid. Well, topologically, it's a sphere. But that means, and we've mentioned before, spheres have positive curvature, and they're not very stretchy. At least I hope they aren't.
What, oranges?
The peel on them shouldn't be.
Oh yeah, no, yeah, that sounds like some Black Mirror oranges.
Yeah. So yeah, if you peel it and you're good enough at peeling an orange to keep it in one contiguous piece, and if you try to flatten it out onto a table, it won't really flatten all the way, like you said, without cracking some. And that's because, so if you could flatten it, it would have 0 curvature, right?
Yes.
But if an orange is spherical, it has positive curvature. So you can't, without stretching it, turn it from positive curvature to 0 curvature.
Yeah, and in the same way, if you tried to squish a saddle onto the ground, it would be like you would have to kind of like push it together almost. It would bunch up like the surface of a saddle, right?
Yeah, so a saddle isn't going to get flattened on the ground either without, probably without seriously damaging it.
All right, so we move on from oranges to pizza.
Yeah, so this is the fun thing about, so the Theorema Egregium can be used as a strategy for eating pizza, because don't you just hate it when it's like you're trying to eat pizza, but it's like you don't want to use both hands necessarily to hold it up. But if you hold it with just one hand, then it might droop down.
That's like if you're holding the crust, right?
Yeah. So let's think about what pizza is. So it's just a disc, a flat disc.
So pizza has 0 curvature, right?
So But pizza can bend, right? So let's say we have a slice. So we take a slice, still has zero curvature, and then we lift it up just by the crust. So it's going to droop down, right?
Yes.
Yeah. So that's gravity doing its work. And so what's happening is it's bending but not stretching.
Yeah,
At
pizza
least
isn't stretchy.
I would hope it not. I would hope not. Otherwise,
Put it back in the oven.
Yeah. But anyway, so what happens then so let's say that we hold the pizza such that we're bending the crust.
Kind of like a New Yorker.
Yeah. So just fold the pizza in half, kind of like into a calzone shape. So it'll be curved along that axis. So from the crust to the point of the slice. So what's that going to look like then?
It's gonna just be a straight line, right?
Yeah. So the pizza will actually hold up. It won't droop down.
Yeah, and the reason why it can't droop down is because if it could, it would be a negative curvature.
Right, and it would require some sort of stretching of the pizza, which again, put it back in the oven.
And stretching in terms of material science means that you're actively deforming or like you're messing with the bonds between things, right?
Just change the axis that the curvature is on, and because it's zero, it'll make it easier to eat your pizza. So just eat your pizza like a New Yorker.
From Euclid to Gauss, circles to saddles, and pizza to parametrization, we have explored the concept of curvature as it relates to complex surfaces. This concept of curvature was essential for developments in physics, such as general relativity, and is an essential component of a differential geometry arsenal. I'm Sophia.
And I'm Meryl.
And this has been Breaking Math. It's been a kind of cool episode. One thing that actually kind of directly relates to this episode is the poster we keep plugging, $19.65, facebook.com/breakingmathpodcast. Click on shop. All right. Till next time. Actually, I don't even know. Robespierre was a complex person, but this is a math podcast. And he was terrible.